added to the system another particle k, number 3. So you will have this interaction. Another step will be, except that you will add one more particle. So you will have this interaction. This, how many you will have? These also, these. That's true? That's all? No. Also these two. Yeah, interaction. 2 by 2. Yes. Can you guess if you have n particle, how many interaction we can have? If I, it will be, yeah, it will be the choose of the 2 among n. In mathematics, you know, n factorial, 2 factorial, n minus 2 factorial, n minus 1 over 2. I don't use any statistical mechanics here. This is just about the how many possibility for selecting the 2 if you have more than, if you have n number of the particles. Yeah, this is a famous approach. Binomial theorem. Is it work here? Yes. If you have a 3, so let me to check a 3 minus 1 over 2. 3 option, yes. 2 minus 1 over 2 will be 2, will be 1 option, just yes. And here, 4 minus 1 over 2, 2 minus 3 will be 6. We should have 6, 2, 3, 4, 5, and the 6. 4 particles, yes, we have 6. Maybe it was better if I put this particle also like here, that make the clear, more clear. So they interacted, these interacted, and these interacted, and how many we have? 6. Yes, that's better. And you can continue that. So, tell me how many of these you will have. Total, what is the total variance? So, V total will be sigma V ij. And for each one you have this term, so, because the form of the potential is the same for all of them. Just you have this factor here for the counting of the number. N is a bit large number, yes, as usual. So there is no difference between n minus 1 and n. So let me to write this n squared over 2 just. R partial is this. So this is the total variable, but not the work doesn't finish. So if you want to use the expectation value theorem, you remember I derived the equation of a state for the gas before using the variable. But what you did was the expectation value, because you're required to use the equipartition theorem. Next step is just consider the average of this quantity. Average of this quantity. Average is minus n over 2 r partial. If you can calculate that very easily from the previous calculations, and this is a hard part actually, this is our hard part. If you can calculate that, this variable should be equal to the what? To the minus 3n per t, I can remember. It should be equal to that, like the non-interactive gas. And from here you can get the equation of state. And this will be proportional to the pressure. Anyway, I wanted to calculate this average. Let me don't write that first. We just are going to calculate this. Okay, so this is the average. So you know how to do the averaging, so for the normal function. So here we have the similar, so this is like a normal function. So, but the problem is that the r, so this r is a vector r2 minus r1. For any averaging you needed to make the integration. So f a r actually should be integral of f a r some density function, which is called density weight function. Yes, exactly. D cubic r, because this is a volume over the total volume. So something like that, they will give you the average. This is a normal averaging. It's not a statistical average or something. This is a normal averaging. You needed to have the density and multiply the density to the function and just make the integral. Why you have a double integral here? Because this r is not just one r, it's r1 and r2, so you needed to write two volume here. This is a 6-dimensional normal integral actually. So the variable which you are looking for, that we call it V interaction. This, because you have integration. So will be minus n over 2, the integral of r partial derivative of this with respect to r dr d cubic r d cubic r2 over volume. Only when the potential is a function of the r, you can calculate this integral. Otherwise, the integral will be very complicated. If you consider the potential as a function of the direction or the angle, so that will be very difficult. This is a very commonly mistake in many works actually. So I wanted to develop a method to calculate this integral. So the best way is that you change the coordinates. So you can use a system of the coordinate. Okay, this is about the r, you needed to keep it this, because if you change this r to another coordinate, so your potential will be another function, so it will be more problem for you. You know u as a function of r, you don't know u as a function of, for example, like c or another coordinate like x. And I use this coordinate, but you can imagine what's the second coordinate. This is the location of the center of the mass. So I pass from the two-body system to the centrifugal centrifuge. This big vector is r1 plus r2, if you just remember the vector notations. So r1 plus r2, half will be, I don't know, will be here. So this is the center of the mass. Anyway, you don't need this picture, just to be sure that this is the center of the mass. I made this picture. Center of the mass exists here, like this point. So we use these coordinate systems. You need to know that how to change the volume integral from this to that. dr1, dr2, or d cubic r1, d cubic r2 will be the Jacobian of the transformation from r1, r2, r and r, dr, dr. What is this Jacobian? This Jacobian is call it the Jacobian of the transformation r1, r2, r and r. Partial over the r1, partial. be careful when you write this, because you cannot take the derivative of the vector with respect to the vector. No? This is actually coordinate by coordinate, but I don't want to write the matrix in how many? 6 multiplied to the 6. 6 coordinate here, 6 coordinate here, 6 coordinate. So you need to write 6 multiplied to the 6. I don't want to write that. I write in the vector form as a, well, as a, this is a accepted things in the writing. So partial r with respect to r1 will be -1, and partial this is +1. Partial r with respect to r1 will be 1/2, and 1/2. So that will be -1/2 minus 1/2 will be -1. Of course, nobody write the volume in the negative. So always we define this, as you can find in the Arfgen, we write this in the absolute value. Changing the volume sign is not welcome, actually, but it happens. In cosmology, normally it happens. When the phase of the matter change from the one phase to other phase, to the volume of the phases will change. They call it signature changing. So anyway, so let to make little acceleration to our work. So what is that? So we can pass from dr1, dr2, or I write everything in double form. So I want you be sure that dqr, dq, dr, dr. No, same notation. What is the volume of that? So it will be 4p r squared dr multiplied to d cubic r. So you have everything. So now I inserted that in the integral. So V interaction variable will be minus n over 2a integral r partial r dr gr 4 pi r squared dr integral d cubic r over the volume. Over the volume, yes. So do you think this equation has something missing or no? This equation. This is correct, this is correct, this is correct. That's here. I see that you have a volume here, so you have one V. And next particle also have V. So we needed to write one V more. Can I write this V square? So this is one V, the integral of cubic r. One of the V is here. So one V will be cancelled by that. So minus n squared 2n integral n. Okay, but still this integral is very hard to calculate because you needed to know the distribution function gr. As long as you don't have gr, you cannot evaluate the integral. Let's think how to evaluate this integral. So to evaluate the integral, you need the density. So you need the density function from quantum mechanics. Do you know what is that? This is a side of the system, if you have it. But you don't have the potential. How you can find the side? Because to find the side, no, you have a potential, but it's very difficult to find the side for the two particles. You never can do that very easily. Anyway, we just have the idea about the G. So G is the psi square. Is the density of the particle. Finding the particle 1 in the coordinate r1 and finding the second particle in the coordinate r2. So this is exactly psi 1, 2 square. but this is actually psi R1 and R2, but because the wave potential is centrifugal, so it will be something like psi R12 and the R square. You see that it's and because centrifugal doesn't move, so it will be psi R1 minus R2 or R2 minus R1, okay? The wave function for the centrifugal, yes? Wave function doesn't move, mean classical doesn't. But in quantum mechanics, the wave function for the centrifugal is considered as a plane wave. I mean, it's just defined by the total momentum of the system. So this is like the free particle in quantum mechanics. So it's proportional to EI P dot R over H bar. So you know that the square of exponential is 1 when you have I. Anyway, you need to know that finally, if you want GR, you need to know the sign, but you don't have the sign.
Doctor, isn't inside the integral R cube?
Where?
GR R cube, because you have 4 by R squared and R du over du.
Yes, 4 pi is here with n square and 2 is here. GR is here, RU or DR. You have 1 R square. Yes, you're right. Thank you. R cube. We need to find this integral. Find means that to consider some type of the G and evaluate the integral. So this is the virial of the interaction. No? Why we call it the virial of interaction? Because you started by the potential interaction potential. So this is the virial for the interaction. Total virial will be V VR interaction, here virial when there is no interaction. Virial for interaction was, we consider that was minus n squared 2p V integral R cubic GR partial it is dr. Virial non-interaction, it was our first result actually, was minus 3pV. That could be minus 3n per t. This comes from the equipartition theorem, you remember. This is from equipartition. And this is the virial for the non-interaction when you do not have anything. So this is the total virial. So you can play by this equation, I mean eliminate the minus and just find for me the pressure. If you do that, PV will be PV over N per T, will be 1 minus 2P and 3 per T. I try to remember all the equations in writing, but sometimes it's better to see the paper, because if you do the one mistake, it will be go wrong all the system. That's the reason. Normally I don't use the paper for writing some course, but quantum mechanics was my favorite use for electromagnetics. But here there is a very risky actually things to do. So what is the range for the R? Oh, this is very problematic. You never can write the zero here for the limit of the integral, because what is the R? R is the distance between the particle, I and the J. You never can set two particles close together. You can make it close, but not very much close. So it's better to write it this something else, but in limit, actually, you can make it very close down to it, very close, in the limit, in mathematical. I write it 0 plus, it will start after the 0. It's not real 0. But the particle can sit in any distance from each other, any distance. Any distance, I write it minus infinity here. This infinity is not the real infinity. It is just maybe some nanometer or some micrometer. Huh? The size of the particle are 10 power 1 angstrom, for example. This distance can be, I don't know, less than 1 millimeter or something. It will be